Wherever the least energy is present, this mark will be there. If it is the equivalent, we will show in equals. If the protons will keep on increasing, the attraction between the electrons and the protons will increase. Spin quantum number, one will be plus half and another will be minus half. By that, we can conclude that no two electrons in an atom can have the same set of 4 quantum numbers. Hello everyone, this is Harshita Bhavsar from Vidhyaashram PU College, Temple of Excellence. Today we are going to have a last session on the chapter, that is structure of atom. Okay, in the last session we have seen orbitals and quantum numbers and shapes of atomic orbitals. We have seen the atomic orbitals have came into the concept and the quantum numbers and what are the shapes of atomic orbitals. In this session, we will have electronic configuration of atoms and filling of orbitals in an atom, stability of completely filled and half-filled subshells. Okay, let us see the energy of orbitals. The energy of an electron in a hydrogen atom is determined solely by the principal quantum number. Thus, the energy of the orbitals increases as follows. See, we have seen in the last session that principal quantum number will determine the energy of subshell. When the n value will be increased, automatically that energy of the orbital will also increases, right? Thus, the energy of the orbitals increases in 1s is the least energy comparative to 2s energy. This will be 2s and 2p will be same energy. It is having the equivalent, so it is having same energy. Again 2p is less than 3s. 3s, 3p, 3d are having same energy. 3d is less than 4s. 4s, 4p, 4d and 4f are same and it will be keep on moving. Wherever the least energy is present, this mark will be there. If it is the equivalent, we will show in equals. Okay. The orbitals having the same energy, whichever the orbitals having same energy like this are called degenerate levels. Okay. Example, shapes of 2s and 2p orbitals are different. An electron has the same energy when it is in the 2s orbital as when it is present in the 2p orbital. See here, 2s and 2p are having same energy, they are telling. And another thing, they have given only about hydrogen atom. Okay. First, what we have to understand means hydrogen will be having only one electron in 1s orbital. If it is only one electron, if it is a nucleus, this is its orbit, this is its electron, only one electron. In this, only one electron is present. That's why the interaction between proton and electron will be the attractive interaction. Okay. Here, the interaction will be in an attractive way. If any multi-electron system is present, means here one electron, here one electron and here also electrons are present. Some of the attractive interactions also we can see, and here we can see a repulsion because electron-electron interaction means like charges interaction, that time repulsion will take place. In this, both attractive interaction and repulsive interaction we can see. Okay, in multi-electron system, in only single electron system, attractive interaction will be seen. Okay. Why these we are talking about interactions means based upon the stability of an atom. When attractive interaction of the atom increased comparative to repulsive interaction, then the atom will be stable. Okay. And the energy of atom or the energy of orbital will be determined by two quantum numbers, that is principal quantum number and azimuthal quantum number. Principal quantum number will be designated by n and azimuthal quantum number will designated by L. Okay, by these two quantum numbers we will be having the rule, that is n plus L rule. This rule helps in comparing the relative energies of two orbitals. Okay, by the two orbitals we have done the comparison between two orbitals with respect to energy. According to this rule, the lower the value of n plus L for an orbital, the lower of its energy. When the n plus L value is low, that time its energy will be lower. If two orbitals have the same value of n plus L, if the two orbitals having the same value of n plus L, then we have to consider the orbital with lower value of n. Okay, we will have the lower energy. If the n plus L is value which same, we have to see the n value. In the n value, if we have lower value, then we have to consider that n value will be having lower energy. To understand better, we will see this table. Okay, the orbital 1s will be having value on n is 1, value on L is 0. The value of n plus L, 1 plus 0 will be 1. 2s orbital, value of n is 2, L is 0, 2 plus 0 is 2. 2p orbital, 2, 1, n is 2, L is 1, 2 plus 0 is 3. While comparing these two, see here, this n plus L value is more than 2 than 1. So, 1s, least energy, 2s and 2p. Okay. See here, 3s, n equal to 3, L equal to 0, 3 plus 0 is 3. In 3p, n is 3, L is 1, 3 plus 1 will be 4. That time 3p lesser than 3p. Okay. Then 4s, in 4s orbital, n is 4, L is 0, 4 plus 0 is 4. In 3d, n is 3, L is 2, 3 plus 2 is 5. In this also we can tell 4s is less than 3d. Okay. Next, when we compare to 3d and 4p, see here n plus L value is same, means 5 and 5. That time we have to consider the n value, which is the higher value comparing to 3d and 4p. This 4, that is the n value is more, that time 4p is greater than 3d. Okay, like this we have to assign the n plus L rule. Next we will see the shielding effect and effective nuclear charge. First we will see effective nuclear charge. In an atom, the electrons are attracted by the nucleus. The greater the number of protons in the nucleus, stronger is the attraction. The net positive charge experienced by the electron from the nucleus is known as effective nuclear charge. Okay, if this is the nucleus, this is orbit. In nucleus we will be having protons, right? Here electrons. Here also electrons. If the protons keep on increasing, the attraction between the electrons and the protons will increase. That's what they are telling, that greater the number of protons in the nucleus, stronger will be the attraction between the protons and electrons. Okay, that complete attraction experienced by the electron, we'll call it as effective nuclear charge. We'll see shielding effect. The nuclear force of attraction on the outer electrons of the atom is lowered by the electrons present in the inner shell. This is called shielding effect or screening effect. So, due to this screening effect, the net positive charge experienced by the electron from the nucleus is lowered. Okay. We can see in the same thing. This is nucleus. This is orbit. Okay, here also electrons will be present. Here also electrons. Okay. Protons will attract electrons, but this will experience more attraction. Okay. This is the outermost shell. It will also experience the attraction, but less when comparative to inner shell. Okay. And also this inner shell electrons, whatever these inner shell electrons will avoid or will act as a screen to avoid the attraction between the protons and the outermost electrons. It will act as a shield in between protons and outermost electrons. This effect we'll call it as screening effect or shielding effect. Okay. Next, electronic configuration. The distribution of electrons in the orbitals of an atom is called its electronic configuration. The overall electrons, how it will be distributed in an orbitals of an atom, will call it as electronic configuration. The electronic configuration of different atoms can be represented in two ways. That is, first S to the power of A, P to the power of B, D to the power of C. It is a notation. For that, we have to see this energy level diagram. First, we have to represent S, then 2S, 2P, then 3S, 3P, 4S, 3D, 4P, 5S, like that, 4D, 5P, 6S, then 4F, 5D, 6P, 7S, then 5F, 6D, 7P. Like this only we have to represent our electronic configuration. First we will see this notation by having an example. We will see carbon. Carbon atomic number is 6, 1s2, 2s2, 2p2. See here 2, 4, 6. Okay, overall 6, 1s2, 2s2, 2p2. And we have to understand that each orbital can accommodate 2 electrons only. Okay, means each shell can accommodate, subshell will have maximum number of 2 electrons. We know that S will be having 1 shell, P will be having 3, D will be having 5, F will be having 7. Correct? 2 electrons means 1 into 2, 2, 3 into 2, 6, 5 into 2, 10, 7 into 2, 14. The capacity of these subshells, the capacity of electrons containing in these subshells is for S, 2, for P, 6, for D, 10, for F, 14. Okay. That's why here S is 2, S is again 2, P, why we have not written 6 means it should be correlate with atomic number, the existing number we have written. 1 to 6 we can accommodate in P. Okay. In next notation is orbital diagram. In orbital diagram, it is the second notation. Each orbital of the subshell is represented by a box and the electron is represented by an arrow, a positive spin or an arrow, a negative spin. Okay. See here, it is a box representation of electrons. We can write S, P, one, 2, 3, 4, 5. This is S, this is P, this is D, and again F. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is F. The sublevels, how we have written, S contains 1 level, P contains 3 levels, D contains 5, F contains 7. Like that we have written here. Lithium C, atomic number 3. Each shell contains 2 electrons and it should be as a opposite spin. If it is one is positive, another one will be negative. 1, 2, 3. Beryllium 4, 1, 2, 3, 4. Boron 5, 1, 2, 3, 4, 5. Carbon 6, 1, 2, 3, 4, 5, 6. Nitrogen 1, 2, 3, 4, 5, 6, 7. Here we will tell this is Px, Py and Pz. 3 orbitals of P shell, we know that P subshell, and we have to, why we have filled like this, we will see in the next slide. Okay, first we will see here oxygen 8, 1, 2, 3, 4, 5, 6, 7, 8. Fluorine 1, 2, 3, 4, 5, 6, 7, 8, 9. And neon, it will be 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Why this Px, Py, Pz have singly occupied one side, double occupied another side? We will tell. Filling up of orbitals in an atom. In the ground, first we will see half bow principle. In the ground state of the atoms, the orbitals are filled in the order of their increasing energies. Those we have seen in the electronic configuration concept, how from the lower energy, it will be keep on filling up to higher energy. Means that in the increasing order of their energies, it will fill their electrons. That is the half bow principle. Next, Pauli's exclusion principle. No two electrons in an atom can have the same set of 4 quantum numbers. There are 4 quantum numbers. Each shell will be having 2 electrons. Between 2 also will be doesn't have, it should not have the same quantum number. If we take 2s, 2p like that, if we take carbon only, okay, 1s2, 2s2, 2p, 2, right? We'll take 2s and 2p. 2s, 2p. What will be the n here? 2, L will be 0, M will be 0, S will be plus half or minus half. Here n equal to 2, L equal to 1, M equal to plus 1, 0, minus 1, S will be equal to again plus half or minus half. Okay. Here 2 orbitals we have seen. See, both are same, n will be same, but see here L will be one side 0, why? S value L will be 0, P value L will be 1. Here only both are different, again M will be different. Again if we take in this same 2s only, okay, in 2s 2 electrons will be present. We will be having all same things here, but in the spin quantum number, one will be plus half and another will be minus half. By that, we can conclude that no 2 electrons in an atom can have the same set of 4 quantum numbers. One of the quantum number will be different from one another. Okay. That is the Pauli exclusion principle. Next, Hund's rule of maximum multiplicity. What does it mean? Pairing of electrons in the orbitals belonging to the same subshell P, D or F does not take place until each orbital belonging to that subshell has got 1 electron each, that is, it is singly occupied. By reading this, you will not understand correctly. See this table. We'll take so many elements. By that electronic configuration, we will understand the Hund's rule of maximum multiplicity. Element is boron. The atomic number of boron is 5. Okay, we'll see the electronic configuration 1s2, 2s2. In s orbital, there is no problem. See here, they have told p, d, f. In s orbital, it will have 2 maximum electrons. In p orbital, 1, 2, 3, 4, 5. It will be 2px, 2py, 2pz. Okay. Carbon, 6 atomic number, 1, 2, 3, 4, 5, 6. Okay. 7 nitrogen, 1, 2, 3, 4, 5, 6, 7. You can tell why we are not adding here, then rather than adding here. It will be wrong. That does it mean of Hund's rule. They are telling these 3 sublevels of p orbitals should first accommodate singly. See here, 1, 2, 3. Then it is getting occupied to same px level. Till it occupied its all levels, it will not accommodate the previous level. Okay. See here, in oxygen 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then in fluorine 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Neon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like that. After all, it is coming to add up here before levels. Till it occupied all single levels, it will not occupy the previous level. That it means the pairing of electrons in the orbitals belonging to same subshell does not take place until each orbital belonging to that subshell has got one electron each, that is singly occupied. Next we will see the stability of half-filled and completely filled subshells. A set of orbitals of same energy is highly stable when all these orbitals are either completely or half-filled. Okay, if the levels are completely filled or half-filled, then the atom will be stable. We will see with the example. Chromium atomic number is 24. The expected configuration, what we will expect by seeing or by reading the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. Because 4s2 is least energy, we will see like this. It is an expected configuration, but these two are what? Exceptional cases. But the actual configuration of the chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s1. Okay, if we see here 1, 2, 3, 4. This is the D level. 1, 2, 3, 4. Here 4s2 is completely filled. For 3D becoming half filled, it will jump one electron to D subshell. Thus, it will become 3d5, it will become 4s1. D level will be half filled. The electron exchange will takes place. Okay. For copper, 29 is the atomic number. Expected configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s2. Okay. The actual configuration is same thing. Here, if we see, same, the electron will exchange from 4s2 to 3d9, then the 3d10 will be completely filled. Okay. Same thing. 5, 6, 7, 8, 9. Till that it was cleared. Only one electron was missing to have a complete configuration. For that, it will jump from 4s2 to 3d9. It will become 3d10. Okay, this is also D subshell. So here half shell filled, this is completely filled. In these two cases, the stability of atom will be more. Okay, that is what the stability of half filled and completely filled are being explained. Why it is being explained out means, here two concepts or two reasons are behind. That is, one, symmetry of an electron. See here, all are in symmetrical. Here also all are having symmetry. And another one, energy exchange. For about energy exchange, you will read in your higher classes. By seeing this only, you can understand the symmetry. Symmetry means from every side it will look same. From here also it will look same. See, 2 electrons, 2 electrons, 2 electrons with opposite spin. Here also all the shells are completely filled with single electrons. Okay. These are the two reasons for the stability of the orbitals. By this, we are ending up with the chapter. I hope you have understood the all session. Thank you so much. We will see in the next chapter.